Hello, welcome to the Cosmic Guide to Sleep. This is where curiosity meets tranquility. From the moment humanity first gazed up at the night sky, that planet glowing with crimson light captured our attention. In the myths and legends of ancient civilizations, Mars was often seen as a symbol of war and power, yet it also represented a distant possibility, a dream of another world existing within our collective imagination. With the dawn of the space age in the mid-20th century, this dream began its journey from myth to science. We launched our first probes to Mars. They returned blurry yet ominous inspiring images of a strange, created world. From that moment we knew Mars was not a hostile deity, but a real planetary world, a new frontier awaiting our exploration. Over the following decades, our robotic emissaries pressed forward relentlessly. From flybies to orbiters, from landers to rovers, our understanding of Mars grew exponentially. We discovered dried riverbeds and polar ice caps. We analyzed its atmospheric composition and soil structure. Each step deepened our conviction that Mars is the solar system's most Earth-like planet for human visitation. Yet these explorations were merely prologue to a grander narrative. Our dream has never been merely to send robots to photograph and analyze. We dream of setting foot upon that crimson soil ourselves, to witness Martian sunsets with our own eyes, and touch its sun-zoned rocks with our own hands. This dream has driven generations of scientists and engineers. It is not merely curiosity that compels us. It is rooted in humanity's innate drive to explore the unknown, an extension of the force that spread our species across the globe, now reaching cosmic scales. Today, the centuries-old dream stands on the brink of realization. Technology is maturing. The vision is sharpening. We no longer seek merely to visit Mars. We plan to stay there. This is the most ambitious adventure in human history, and our first step toward an interstellar civilization. As the global leader in space exploration, NASA has long designated crewed Mars landing as its North Star goal. This objective did not arise in a vacuum. It rests upon a meticulously phased, long-term plan, whose core logic is incremental, step-by-step progress. The Moon has been designated as the critical testing ground for Mars. Through the Artemis program, NASA aims to return astronauts to the Moon in the 2022s, establish a gateway space station in lunar orbit, and build sustainable outposts on the lunar surface. Why return to the Moon first? Because the Moon is the ideal platform for testing all critical Mars technologies, including life support systems, habitat construction, In-Situ resource utilization, and deep-space communication and navigation. All technologies validated on the Moon will be directly applied to future Mars missions. Beyond technology verification, lunar missions also help us understand the physiological and psychological challenges humans will face in deep-space environments far from Earth. While the Artemis program advances steadily, NASA's Mars Design Reference Mission architecture continues to refine. This blueprint details the entire process from Earth departure to Mars and establishing long-term surface habitation. It encompasses every detail from spacecraft design and propellant selection to mission sequencing and surface infrastructure. This endeavor is not solely NASA's initiative, but a truly global collaborative project. The European Space Agency contributes critical propulsion modules and module designs. The Canadian Space Agency provides advanced robotic technologies. The Japan Aerospace Exploration Agency brings expertise in life support and cargo transportation. Additionally, participation extends to leading global research institutions and commercial enterprises. For instance, SpaceX's under-development Starship is considered a strong candidate for future Mars cargo and crewed missions. This model of international cooperation is crucial because it not only distributes the enormous R&D costs and risks, but also pools the world's most advanced intellect and resources, making such an ambitious goal financially and technically feasible. NASA's plan is not static. It is a living document. With each new discovery from robotic missions, and with every technological trial's success or failure on Earth, it undergoes continuous refinement and optimization. For instance, The Perseverance rover's exploration of G0 crater has profoundly deepened our understanding of Martian geology and ancient environments, while providing crucial data on its suitability as a future landing site. These relentless scientific and engineering endeavors serve as solid stepping stones, gradually propelling us toward that decisive moment when all conditions are ripe. When all systems are ready, the first human explorers will bid farewell to Earth, embarking on the long journey to Mars. Why Mars? Our solar system holds many other captivating worlds. Venus boasts a dense atmosphere. Europa may conceal vast oceans beneath its icy crust. Yet Mars possesses a unique combination unmatched by other planets. Its Martian day closely mirrors Earth's. A Martian day lasts approximately 20-4 hours and 30-9 minutes. This means astronauts' biological clocks would experience minimal disruption. Mars exhibits distinct seasonal changes. Though each season lasts twice as long as on Earth, it provides a familiar temporal rhythm for long-term habitation. Most crucially, Mars possesses the essential resources for life, particularly hydrogen and oxygen, abundant in the form of water ice. These resources form the foundation for sustaining life and producing fuel. Viewing Mars as humanity's second home means we are seriously contemplating a future beyond Earth. Earth is our only home. It is beautiful and precious, yet historically, putting all our eggs in one basket has proven risky. Asteroid impacts, supervolcanic eruptions, or global climate upheavals have all dealt devastating blows to life on Earth. Establishing a sustainable Martian community is like purchasing insurance for human civilization. It ensures that even if Earth faces a global catastrophe, the flame of human wisdom and civilization can still endure in the cosmos. This does not mean we abandon Earth, quite the contrary. Learning to sustainably survive on Mars, in a closed, resource-limited environment, will provide invaluable experience and technology for better managing our home planet. From efficiently recycling every drop of water to producing food in harsh conditions, this knowledge will flow back to Earth to benefit all humanity. Becoming a multi-planetary species fundamentally reshape humanity's self-perception. When we gaze back at Earth, that fragile blue planet, suspended in the pitch-black expanse of space, we may grasp more profoundly our shared destiny as inhabitants of one common home. Mars will transcend being merely a scientific outpost or technological marvel. It will become a symbol of human courage, wisdom, and collaborative spirit, a starting point toward the vast cosmos. On Earth, we are accustomed to instant gratification. Messages received near-instant replies. Journeys are planned in hours or days. But for Mars missions, we must first abandon this Earth-centric mindset entirely. The distance between Mars and Earth is not fixed. As both planets orbit the Sun along their respective paths, their separation constantly shifts. At its closest, they are approximately 50 million kilometers apart. At their farthest, the distance can exceed 400 million kilometers. The most immediate challenge posed by this distance is communication delay. Radio waves travel at the speed of light, circling Earth 7.5 times per second. But when journeying to Mars, they embark on a lengthy voyage. When Earth and Mars are at their closest approach, a signal still takes about 3 minutes for a 1-way trip. When the planets are on opposite sides of the Sun, this delay skyrockets to over 20-2 minutes. This means sending a simple greeting from Earth to Mars, like "Hello, how are you?" can take up to 20-2 minutes to arrive. Receiving the reply "Hello, I'm doing well," then requires another 20-2 minutes. The entire exchange consumes nearly 40-5 minutes. Such delays render real-time conversation entirely impossible, fundamentally altering the interaction model between mission control and astronauts. Ground control centers will be unable to monitor and direct every astronaut's action in real time, as they do during International Space Station missions. When astronauts on Mars encounter an emergency, such as equipment failure or a crew member injury, they cannot immediately call for guidance from Earth. They must make decisions and take action independently. During those 40-4 minutes of signal round-strip time, the situation could change dramatically. This communication delay also profoundly impacts astronauts' psychological state. Their interactions with family and friends will no longer be seamless video calls, but more akin to sending and receiving lengthy emails. This near-minus complete disconnection from Earth society and the profound sense of isolation reaches levels unprecedented in any previous space mission. To address this challenge, the entire mission architecture must be redesigned. Systems at the Mars base must possess extreme autonomy, capable of independently handling the vast majority of daily operations and emergency malfunctions. The astronauts themselves must be trained as true explorers and problem solvers, rather than mere executors of commands. They need to master cross-disciplinary knowledge, from equipment maintenance to emergency medical care, to ensure self-efficiency during crises. Meanwhile, mission planners are designing a complex communication network by deploying multiple relay satellites in Martian orbit to build a local Martian internet to ensure seamless connectivity between surface sites and orbital spacecraft. While communication with Earth remains delayed, information can flow rapidly within the local Martian network. This self-sustaining network represents the first step toward a self-sufficient Martian community. If distance was Mars' first challenge, then its atmosphere and climate present an ongoing severe test. Mars possesses an extremely thin atmosphere, with surface atmospheric pressure less than 1% of Earth's average C- level pressure. What does this figure mean? It means that if you stood on the Martian surface, the atmospheric pressure you'd experience would roughly match the pressure at an altitude of 35,000 meters on Earth. This altitude is more than 3 times the cruising altitude of Earth's commercial airliness. In this near-vacuum environment, a human without a pressurized spacesuit would lose consciousness within seconds and die within 2 minutes. This extreme low pressure also means sound cannot propagate effectively. The Martian surface would be an exceptionally silent world. Mars' atmosphere is composed of 95% carbon dioxide. The remainder consists of trace amounts of nitrogen and argon, and negligible amounts of oxygen. This means humans cannot breathe Martian air directly. Far from sustaining life, it is a suffocating gas. More alarmingly, Martian air is laden with vast quantities of dust. This dust is incredibly fine, finer than flour, and due to electrostatic forces, it adheres to any surface. This includes solar panels, optical instruments, and the joints of spacesuits, causing equipment degradation or failure. This dust also carries perchlorate ions, a chemical harmful to thyroid function, which, if inhaled by astronauts, would severely jeopardize their health. Mars' thin atmosphere barely retains heat, causing extreme fluctuations in surface temperatures. During a typical Martian day, midday temperatures near the equator might barely reach 20 degrees Celsius above zero, creating a fleeting illusion of warmth. Yet by nightfall, temperatures plummet below -80 degrees Celsius. This extreme environment, with daily temperature swings exceeding 100 degrees Celsius, poses a brutal test for all materials and equipment. They must endure countless cycles of expansion and contraction, without warping or cracking. The most iconic feature of Mars' climate system is its global dust storms. These storms are unlike any gales we witness on Earth. Mars winds, even at their fastest, remain limited in force due to the thin atmosphere. They cannot uproot trees like Earth's hurricanes, yet they are potent enough to stir vast quantities of fine dust. Once stirred, this dust can remain suspended in the atmosphere for weeks or even months. A regional dust storm can escalate into a global event engulfing the entire planet. At that point, reed dust obscures the sky, dimming the midday sky to twilight-like gloom. The 2018 mission termination of the Opportunity rover was caused by just such a global dust storm. Thick dust blanketed its solar panels, cutting off its power source and ultimately sending it into a permanent slumber in the bitter cold. For solar-dependent outposts, this is undoubtedly a deadly threat. During dust storms, sunlight is drastically weakened. Solar power generation may plummet to less than 10% of normal levels. Without a robust and reliable backup power source, life support systems risk shutdown. Additionally, electrostatic activity in the air becomes exceptionally intense during dust storms. This can disrupt or even sever radio communications, leaving astronauts on the Martian surface isolated and helpless. When urgent contact with Earth or orbiting spacecraft is needed, the combined characteristics of the Martian atmosphere paint an extraordinarily harsh picture. It provides neither breathable air nor temperatures suitable for human survival. Its dust is pervasive and toxic, its storms capable of engulfing the entire planet and blocking sunlight. All this means that on Mars, any activity exposed to the natural environment is an extremely dangerous endeavor. Every habitat we construct, every rover we deploy, every spacesuit we wear must be a robust fortress capable of standing alone against this hostile world. Understanding and adapting to these environmental challenges is the only prerequisite for establishing a foothold on Mars. When our astronauts successfully land on the Martian surface, they will step onto an extremely arid and frigid world. Martian soil, known as regolith, is rich in iron oxides, the very reason Mars appears red. This fine dust blankets nearly the entire planet's surface. Martian dust proves far more troublesome than Earth's sand. Its particles are incredibly fine, almost powder-like. Having undergone billions of years of oxidation and weathering, the particles are sharp-edged and highly abrasive. More critically, this dust carries static electricity, causing it to cling tenaciously to any surface it contacts. Imagine an incredibly fine powder of rust that can infiltrate the tiniest crevices, adhering to solar panels to drastically reduce power generation. It blurs optical lenses when deposited and infiltrates the moving joints of spacesuits, accelerating wear. After every extravehicular activity, astronauts undergo rigorous decontamination procedures to prevent harmful Martian dust from entering the clean habitat. Mars boasts the solar system's most extreme temperature fluctuations. Daily temperature swings often exceed 100 degrees Celsius. At equatorial midday during summer, temperatures may briefly reach a comfortable 20 degrees Celsius. Yet after sunset, heat rapidly dissipates into space through the thin atmosphere. Temperatures plummet to minus 60 degrees Celsius or lower. Under such extreme thermal cycling, materials endure immense stress. Metals expand and contract. Plastics become brittle. Seals may fail. All equipment must undergo rigorous testing far exceeding Earth standards to ensure functionality through hundreds or even thousands of such cycles. More severe than daily temperature swings are seasonal variations. Mars' elliptical orbit around the Sun results in exceptionally long and frigid winters in its northern and southern hemispheres. Temperatures at the poles can plummet to minus 125 degrees Celsius, forming vast sheets of dry ice. These seasonal shifts affect global atmospheric pressure and even wind patterns. Dust storms are among the most spectacular yet dangerous phenomena on Mars. They typically begin during southern hemisphere spring and summer, when solar heating causes air to rise rapidly, swirling vast quantities of dust. A regional dust storm can spread over weeks, eventually enveloping the entire planet. Though these storms feature high wind speeds, their destructive power, due to the extremely low atmospheric density, manifests not in impact force like Earth's typhoons, but in their persistence and vast coverage. Finest particles propelled into the upper atmosphere can block up to 99% of direct sunlight, turning daylight into a gloomy twilight lasting weeks. This is fatal for solar-powered rovers, as we unfortunately witnessed with the loss of opportunity for future bases relying on solar power as a supplementary energy source. This necessitates extremely robust energy reserves or primary power sources unaffected by sunlight, such as nuclear energy. Electrostatic phenomena during dust storms are also particularly pronounced. Friction between dust particles generates powerful electrostatic fields that can cause eerie corona discharges and even disrupt radio communications, further complicating the already delayed Earth-Mars communication. Faced with such surface conditions, our base design must incorporate comprehensive protection Habitats require robust sealing to block dust and maintain internal pressure. Energy systems must be diversified and highly reliable to withstand prolonged dust storm seasons. All external activities require precise planning to avoid potential massive dust storms and ensure all personnel and equipment can be safely evacuated during storms. On Earth, we live within a dual-layered protective bubble. Earth's magnetic field forms the first line of defense, deflecting the vast majority of high-energy charged particles from the Sun and galaxy, while its thick atmosphere provides the second layer of protection, absorbing most remaining radiation and transforming it into the beautiful auroras. Mars, however, is a world almost entirely exposed to cosmic radiation. Billions of years ago, Mars may have possessed a global magnetic field and dense atmosphere, but as its core cooled, the magnetic field vanished, and the atmosphere was gradually stripped away by the solar wind. Today's Mars retains only a thin atmosphere and scattered local magnetic fields. This means astronauts arriving on Mars will be exposed to the constant bombardment of two primary radiation sources. The first is galactic cosmic rays, originating from violent astronomical events like supernova explosions beyond our solar system. These particles are extremely energetic, primarily atomic nuclei. This small size grants them formidable penetrating power. They can easily pass through spacecraft and habitat holes, even penetrating human tissue, to damage DNA within cells. Prolonged exposure significantly increases the risk of cancer, cataracts, and central nervous system disorders. Although the flux of individual particles is low, their persistent background radiation poses the primary health threat during long-duration missions. The second type consists of high-energy particles from the Sun. These originate from our own Sun and typically erupt during solar flares or coronal mass ejections. Such events are explosive and difficult to predict, and can multiply radiation levels on Mars' surface several times over within minutes. If astronauts encounter a strong solar proton event during an EVA, they could absorb dangerous or even lethal doses of radiation within hours. This is why every habitat must include dedicated radiation storm shelters, areas shielded with heavy materials, for astronauts to take emergency refuge upon solar activity warnings to counter the pervasive radiation threat. NASA is exploring multiple protective strategies. Fundamental method is mass shielding, using materials themselves to absorb and block radiation particles. On Mars, the most practical material is Martian soil itself. Future semi-minor subterranean habitats, or covering inflatable habitats with several meters of Martian regolith, can effectively reduce internal radiation doses to relatively safe levels. Another more C-5 approach is active shielding, generating a localized strong magnetic field around the habitat to deflect charged particles like an invisible umbrella. This technology remains in early development, but represents one of the most promising long-term solutions for deep space radiation challenges. Additionally, mission planning will prioritize radiation mitigation as a core consideration by optimizing mission timelines to align flights with periods of high solar activity, when galactic cosmic rays are slightly weakened by enhanced solar winds, and strictly limiting astronaut extracurricular activity time. Mars' radiation environment is undeniably harsh, yet through meticulous habitat design, robust early warning systems, and scientific mission management, we possess the capability to manage risks within acceptable limits, paving the way for human long-term survival on the Red Planet. Safely landing a massive spacecraft laden with cargo or personnel on the Martian surface is termed the 7 minutes of terror by engineers. Within these brief 420 seconds, the spacecraft must autonomously execute a series of complex maneuvers with ballet-like precision, where any minor error could instantly terminate the mission. The root cause of this extreme difficulty lies in Mars's peculiar atmosphere. It is neither as dense as Earth's, allowing sufficient deceleration through air resistance, nor as near vacuum as the Moon's, permitting complete reliance on rocket engines. When the spacecraft plunges into Mars's atmosphere at 20,000 kilometers per hour, The heat generated by friction with the thin gases is staggering. Surface temperatures can exceed 1500 degrees Celsius, enough to melt most metals. Thus, a robust, heat-resistant heat shield is essential survival equipment. After the initial phase of intense aerodynamic deceleration, the spacecraft's speed drops to approximately 1600 kilometers per hour. At this point, a traditional parachute can deploy. Parachutes used on Mars must be exceptionally large and sturdy. For instance, the supersonic parachute used in the Perseverance mission measures 21 meters in diameter, making it the largest and strongest ever deployed on Mars. Yet even this is insufficient on its own. Mars's atmosphere is too thin to provide adequate drag to fully decelerate the spacecraft to zero speed. At an altitude of roughly 1 kilometer above the surface, the spacecraft still descends at hundreds of kilometers per hour. This marks the most critical phase of the entire landing process. This is where NASA supersonic retro-propulsion technology takes center stage. The core of this technology sounds counterintuitive. During the spacecraft's high-speed descent, powerful rocket engines are ignited. Instead of firing downward, they are angled diagonally forward, essentially firing into the oncoming asteroid. This creates a controlled state of chaos, using the rocket thrust to directly counter the spacecraft's momentum, enabling drastic deceleration within a short time frame. This process places extreme demands on navigation and control systems. The spacecraft must continuously sense its position, velocity, and attitude, while precisely adjusting engine thrust to ensure hovering capability and a soft landing during the final phase. SpaceX has pushed this technology to its limits in its Starship project. Starship is designed for powered landing throughout its descent. It relies not on parachutes, but instead relies entirely on Raptor engines during the final descent phase to ignite, adjust its attitude, and land precisely at the designated location. This approach is particularly suited for transporting heavy cargo because as cargo mass increases, the volume and strength requirements for parachutes become impractical. While rocket propulsion offers superior scalability, supersonic retro-propulsion represents a fundamental shift in thinking. It acknowledges the limitations of the Martian atmosphere and opts for a more powerful, direct approach to overcome them. This is not merely an innovation in landing methods, but the very key to establishing a base on Mars. For the large habitat modules, heavy rovers, and energy systems required for such a base, each weighing dozens of tons, only this powerful propulsion landing technology can safely deliver these foundational elements to the Martian surface. A successful landing is merely the beginning of the challenge. As the spacecraft's engines shut down and the hatch prepares to open, the first adversary facing astronauts and robots is Martian dust. This ubiquitous red powder is far beyond comparison to ordinary Earth and ore dust. Its particles typically measure less than 5 micrometers in diameter, thinner than 1/10th of a human hair. This extreme fineness gives it near-minus fluid properties, allowing it to infiltrate every crevice without exception. More troublesome still, Mars' arid environment and constant friction endow these dust particles with significant static electricity. Like magnets, they cling tenaciously to solar panels, optical lenses, and spacesuit visors, severely obstructing vision and equipment functionality. The mineral composition of Martian dust also contains perchlorate S, a chemical harmful to thyroid function. If inhaled by astronauts or carried into habitats via spacesuits, it poses long-term health risks. Yet the most immediate danger upon landing isn't the dust itself, but the dust cloud stirred up by rocket engines nearing the surface. Engineers call this phenomenon a dust devil. When powerful rocket plumes strike Mars' relatively loose surface, they instantly kick up massive amounts of dust due to Mars' low gravity and lack of a dense atmosphere to disperse it quickly. These microscopic particles can be propelled hundreds of meters into the air and drift several kilometers away. These high-velocity dust particles function like miniature and blasting pellets, causing severe abrasive damage to the lander itself and the precision equipment deployed around it. They could even cover solar panels, leading to an energy crisis for the base right from the start. To address this challenge, we must construct a clean landing zone for future spacecraft. This requires building a dedicated landing pad. The solution isn't shipping construction materials from Earth. That would be prohibitively expensive. Instead, we'll employ a local minus sourcing strategy, utilizing Mars' most abundant resource, the soil beneath our feet. NASA's Red Planet Factory project is actively testing a technique called sintering. This process resembles ancient brick minus making methods, but employs cutting-minus edge technology. It employs high-minus powered lasers or microwave beams to concentrate heat onto Martian regolith, melting it partially to temperatures exceeding 1000 degrees Celsius. Upon cooling, the soil solidifies into a hard, dense, ceramic minus or glass minus-like surface. This In-Situ manufacturing technology can build robust runways and landing pads layer by layer by moving the energy source, much like 3D printing. Imagine autonomous robotic systems landing on Mars, decades before the first humans arrive, powered by small nuclear reactors or large solar arrays. Their sole mission is to level the terrain, and then use onboard microwave or laser emitters to melt void, solid landing pads at designated base sites. They might also melt roads connecting facilities and foundation platforms for habitats. When human spacecraft finally arrive, they can land precisely on these artificial rock platforms. Engine exhaust impacts the solid sintered surface, stirring up only minimal dust, thus protecting surrounding critical infrastructure. This technology hands over the bulk of construction work to robots, allowing humans to focus on scientific exploration missions requiring greater intellect and judgment. It represents an entirely new paradigm for extraterrestrial construction. We no longer bring everything from Earth, but learn to think like Martians, using local materials to build our new home. Many years before human astronauts arrive on Mars, a silent and efficient construction revolution will already be underway on the Red Planet. Carrying out this advanced mission will not be humans, but an army of intelligent construction robots. These robots will be humanity's first generation of Martian pioneers. They bear the responsibility of transforming a barren wasteland into a habitable outpost. Their mission checklist is clear and formidable. Level the site for the base. Construct landing pads and roads using In-Situ resources. Assemble pre-delivered habitat modules and energy systems. Test the operational status of all critical equipment. All this work must be accomplished with absolute autonomy. Due to communication delays between Mars and Earth, real-time remote control is impractical. These robots require advanced intelligence and collaborative capabilities. Potential designs include large mobile printers, using microwave or laser sintering to harden Martian soil, multi-armed assembly robots, capable of assembling Earth-delivered modules into complete habitats, and compact reconnaissance and monitoring robots, tasked with quality control and rapid issue detection. NASA is collaborating with construction technology firms like ISRU to test prototypes of these robots on Earth. The company possesses extensive expertise in 3D printing lunar habitats. Their large scale printers can continuously produce sturdy wall structures using simulated Martian soil. This technology will be pushed to its limits on Mars. Robotic construction teams will first establish a sturdy work platform before commencing the printing of the habitat's foundation and walls, and potentially constructing protective walls or domes to provide a secure environment for subsequent precision equipment arrivals. The core advantage of this system lies in maximizing the use of local resources, significantly reducing the weight of construction materials needing transport from Earth, thereby lowering the mission's overall cost and risk. When astronauts finally conclude their long journey to Mars and open the hatch of the lander, they will not encounter a chaotic construction site, but a fully functional base prototype awaiting activation. The power system is already operational, Life support systems have completed self-checks, and the living quarters are warm and bright. This seamless experience relies entirely on years of tireless work by robotic pioneers. They paved the way for humanity, enabling the dream of interstellar colonization to take its first solid step. Once the base's infrastructure is ready, the next challenge for astronauts will be how to move efficiently across this vast world. The Martian base won't be a solitary structure, but an integrated complex comprising energy zones, research areas, resource extraction sites, and living quarters. These zones may span several square kilometers, not to mention sites of significant scientific value requiring long journeys to reach. The lunar rovers used in the Apollo missions were disposable, short-range vehicles. Mars missions, however, require a mobile shelter capable of long-term operation in harsh environments, while ensuring the safety of astronauts. This is the concept behind the pressurized rover. You can think of it as a Mars OV or mobile laboratory. It differs fundamentally from any terrestrial vehicle we know. First, it must be a fully sealed, pressurized environment, filled with breathable air, and equipped with an independent life support system. This means astronauts on weeks or even months long exploration missions need not remain encased in bulky, restrictive spacesuits. They can wear comfortable work suits inside the rover to move freely, eat and rest, much like living within a compact mobile habitat. Second, its propulsion system must be exceptionally reliable. Mars's long nights and global dust storms render solar panels unreliable. Therefore, a pressurized rover would likely utilize hydrogen fuel cells, or more likely, a small nuclear reactor as its power source. Both methods provide continuous, stable electricity, unaffected by weather or day-night cycles, ensuring the rover remains operational under the harshest conditions. In design, the Mars rover will be larger than any lunar rover we've seen. It may require an independent suspension system with 6 or more wheels to navigate complex and varied terrain. The interior will be divided into distinct functional modules, including a cockpit, living quarters, a small laboratory, and an airlock interface, enabling astronauts to enter or exit the rover or conduct extravehicular activities. These rovers will serve as the astronauts' feed for exploration on the Martian surface. They significantly expand humanity's operational radius, enabling in-depth field scientific investigations. They are not merely transportation vehicles, but also serve as the astronauts' home away from base camp, a secure, reliable mobile fortress on the vast and lonely red planet. Producing breathable oxygen on an unbreathable planet is the first fundamental challenge for human survival on Mars. Earth's atmosphere contains 21% oxygen essential for life, while Mars' atmosphere holds a mere 0.13%. Its atmosphere is dominated by carbon dioxide, comprising a staggering 95%. This appears to be a colossal obstacle, yet it precisely becomes the starting point for solutions. NASA's MOXIE experiment pioneers this very solution. MOXIE stands for Mars Oxygen In-Situ Resource Utilization Experiment. It is a golden box roughly the size of a car battery that has operated on the Martian surface alongside the Perseverance rover since 2021. MOXIE's core principle essentially mimics nature's photosynthesis through engineering. The only difference is that it uses electricity instead of sunlight to drive the chemical reactions. Its operation can be divided into 3 precise stages. First comes the collection stage. MOXIE uses a pump to draw in Mars' thin atmosphere. It filters out dust particles to ensure purity for subsequent processing. Next is the critical compression and heating stage. The captured carbon dioxide gas is highly compressed and then heated to nearly 800 degrees Celsius. This high temperature environment creates the necessary conditions for the subsequent chemical reaction. Finally, the electrolysis stage. The high temperature, high pressure carbon dioxide is fed into a device called a solid oxide electrolyzer. An electric current is applied within this device. The electrical energy breaks down the unstable carbon dioxide molecules into 2 gases, carbon monoxide and valuable oxygen. MOXIE then separates these two gases, releasing pure oxygen into the Martian atmosphere, while safely venting the carbon monoxide during the Perseverance mission. MOXIE has successfully conducted multiple oxygen-generation experiments. In each 1-hour operation, it produces approximately 10 grams of oxygen, equivalent to about 10 minutes of breathing air for an astronaut, though seemingly insignificant. This figure holds immense symbolic and engineering validation value. It marks the first field demonstration on another planet of the feasibility to manufacture oxygen using local resources. MOXIE is a scaled -down prototype, while the full -scale system supporting future human missions will be roughly 100 times larger. Such a system would need to operate continuously for about 10 months to produce enough oxygen for astronauts to live on Mars for a year, while also generating part of the oxidizer required for their return rockets. The success of this technology means we won't need to carry all breathing air and most rocket fuel from Earth. This saves hundreds of tons of launch mass for missions and represents a crucial step toward achieving long-term self-sustainability on Mars. The path from MOX, i.e. small-scale experiment to industrial-scale life-support facilities, is fraught with challenges, but the direction is clear. We are learning to breathe like Martians, using the planet's inherent resources to sustain our lives. Water is the source of life and the lifeblood of establishing sustainable bases on Mars. Its importance extends far beyond quenching thirst. Water is essential for astronauts' daily drinking and food preparation, and is key to growing crops for partial food self-sufficiency. When electrolyzed, it breaks down into hydrogen and oxygen. Oxygen is used for breathing, while hydrogen can serve as both an energy source or combined with atmospheric carbon dioxide via the Sabatier reaction to produce methane rocket fuel. More critically, water serves as an excellent radiation shield. Behind water walls and habitats, astronauts gain enhanced protection. Fortunately, Mars is not entirely arid. Water does exist, though largely hidden. It is stored in vast quantities as water ice beneath the Martian surface, particularly in mid-latitude regions. In some locations, pure water ice lies buried just beneath the shallow surface soil. NASA's SWIM project, the Subsurface Water Ice Mapping Mission, has analyzed radar data from multiple orbiters to create detailed maps of near-surface water ice distribution on Mars. These maps serve as treasure charts for future base site selection, indicating where this critical resource can be most easily located and accessed. Extracting this water ice requires a complex system. First, robotic drilling platforms are needed, capable of penetrating potentially extremely hard permafrosts. To reach water-rich strata, the ice mixed with soil is then extracted. The next step involves heating this ice-soil mixture in a sealed furnace to melt the ice into water. This water then passes through filtration and purification systems to remove soil particles and potential chemical contaminants, like perchlorates, ensuring it meets standards for drinking and safe use. Finally, the purified water is stored in sealed tanks for daily base operations. This extraction system requires a stable, robust power source to operate. Both drilling and heating, as well as purification, demand significant electricity. This underscores the critical importance of establishing a reliable energy system on Mars. Nuclear reactors may be necessary to ensure uninterrupted operation of this lifeline. Once a stable water source is secured, a closed-loop water recycling system becomes essential. Every drop of water within the base will be treated as precious treasure. Astronauts' sweat, moisture from exhaled breath, urine, and washing water will all be collected. Advanced water treatment technologies will perform multi-stage purification, including filtration, reverse osmosis, and catalytic oxidation processes, to recycle it into pure, potable water. This system targets a water recovery rate exceeding 98%, far surpassing the International Space Station's current 93%. Only by achieving such high closed-loop efficiency can we minimize reliance on Earth-based resupply and truly achieve water self-sufficiency for the Mars base. From detection and extraction to recycling and circulation, comprehensive water management forms the cornerstone of Martian survival. It connects nearly all systems: life support, agriculture, energy, and radiation shielding. Mastering water means holding the key to unlocking the future on Mars, on a world hundreds of millions of kilometers from Earth's resupply capabilities. Achieving food self-sufficiency is not merely a cost-saving strategy, but a fundamental requirement for survival and independence. Early Mars missions will heavily rely on pre-packaged food brought from Earth, which undergoes dehydration, freezing, and special processing to ensure long-term preservation during extended space travel and on the Martian surface. Yet relying solely on Earth resupply is like depending on a thin, costly umbilical cord, unable to sustain the growth of a permanent base. More crucially, humans crave psychological novelty. Long-term consumption of monotonous packaged foods leads to menu fatigue. Even with sufficient calories, astronauts may lose appetite due to boredom, resulting in weight loss and low morale. Therefore, establishing a reliable food production system is key to maintaining astronauts' physical and mental health. The core of this system is creating a controlled environment agriculture module, an artificial oasis completely isolated from Mars' harsh exterior. Here, temperature, humidity, light, and carbon dioxide levels will be precisely regulated, the optimal range for plant growth. The technologies most likely to dominate Martian agriculture are hydroponics and aeroponics. Hydroponics allows plant roots to be directly immersed in a nutrient-rich water solution without soil. This method is extremely water-efficient, as water can be recycled with minimal evaporation loss. Aeroponics takes this further by suspending plant roots in air and periodically spraying nutrient solutions directly onto roots via a fine misting system. This method maximizes oxygen supply and typically yields faster growth rates and higher crop yields. On Mars, water is a precious resource, making aeroponics ultra-efficient water conservation particularly appealing. Astronauts aboard the International Space Station have successfully cultivated various vegetables, such as lettuce, kale, and radishes. These experiments demonstrate that plants can thrive, even in microgravity within enclosed artificial environments. On Mars, with gravity equivalent to 38% of Earth's, plant growth may face distinct challenges, but is anticipated to be more manageable than in microgravity. Scientists are screening and breeding crops best suited for the Martian environment. Candidates must feature short growth cycles and high edible portions with substantial nutritional value. Leafy greens like lettuce and spinach will be the initial targets due to their rapid growth. Next come fruiting vegetables, such as tomatoes, peppers, and cucumbers, which provide additional vitamins and flavor. Longer-term goals include cultivating high-carbohydrate crops, like potatoes and wheat. These are essential for supplying primary energy and achieving self-sufficiency in staple foods. However, cultivating them demands greater space, time, and energy. Supplying plant-based protein remains another critical challenge. Traditional livestock farming is entirely impractical on Mars. The ratio of resources consumed to food produced is too low. Viable alternatives include cultivating edible insects, such as crickets or mealworms. They are rich in protein and fat and offer extremely high feeding efficiency. Another more futuristic technology is lab-grown artificial meat. This involves growing muscle tissue from animal cells within bioreactors. Once perfected, this technology could deliver authentic meat texture and nutrition without harming any animals. The ideal food production system would be an integrated regenerative ecosystem, such as an aquaponics setup combining fish farming with plant cultivation. In this system, fish waste provides natural nutrients for plants, while plant roots and system microbes purify the water, circulating back to the fish tanks. This not only produces plants, but also yields animal protein, forming a small closed ecological loop. Though this system is more complex, it represents the vision of achieving high self-sufficiency in future Martian bases. Caring for these plants on Mars holds significance far beyond mere food production. This green space will become a psychological oasis for astronauts, amidst the monotonous red landscape and confined metal cabins, caring for vibrant plants, observing seeds sprout, grow, bloom, and bear fruit. This process itself possesses profound healing power, effectively alleviating loneliness and stress. When astronauts can pick tomatoes they've grown themselves and savor that long-missed fresh, juicy flavor, the psychological comfort and morale boost in that moment is incomparable to any pre-packaged food. This greenery is not merely their food source, but a symbol connecting them to life itself. A beacon of hope for building a home on an alien planet. In the closed world of Mars, there is no concept of waste disposal, because there is nowhere to dispose of it. Every item deemed waste, whether human waste, packaging materials, or damaged tools, represents precious resources painstakingly transported from Earth. Thus, the core philosophy of waste management is total recycling under use. Every output is treated as a potential resource. First comes the handling of human metabolic waste. This extends far beyond hygiene concerns to represent an opportunity for resource recovery. Astronauts' urine and sweat are already purified and recycled through advanced water-loop systems. Solid waste, however, requires more complex processing. Traditional flush toilets would be a colossal waste of resources on Mars. Instead, drying or compression collection systems may be employed. Collected solid waste, along with organic waste like plant residues, will undergo rigorous composting or biological treatment processes. This process utilizes specific microorganisms or high temperatures to disinfect and decompose the waste, ultimately transforming it into sterile, nutrient-rich fertilizer. This fertilizer can be directly applied to the base's hydroponic or aeroponic farms, providing essential elements like nitrogen, phosphorus, and potassium for crop growth, thus closing the waste loop as a link in the food production chain. For non-biodegradable waste, such as plastic packaging, metal fragments, and discarded electronics, the Mars base would need to establish In-Situ manufacturing and recycling capabilities. Plastics could be cleaned, shredded, and fed as raw material into 3D printers to create new tools or components. Metal fragments could be melted in small furnaces and recast into ingots for subsequent use. This technology is known as In-Situ resource utilization. It enables the base to utilize existing waste and native Martian materials to autonomously produce required spare parts and tools, significantly reducing dependence on Earth-based resupply. Imagine if the handle of a critical valve breaks. Astronauts wouldn't have to wait 2 years for the next launch window's resupply. They could design a digital model and then use recycled plastic or metal powder to print a brand-new replacement part within hours. This self-sustaining capability is a defining feature, transforming Mars bases from temporary outposts into permanent settlements. Ultimately, the entire Mars base aims to emulate a highly simplified Earth ecosystem, where material flows from a closed loop. Plants absorb carbon dioxide and nutrients to grow, providing astronauts with food and oxygen. Organic waste generated by astronauts is recycled into fertilizer to nourish the plants. Discarded packaging, undamaged equipment, or dismantled and remanufactured, gaining new life. This closed-loop system pursues ultimate efficiency, ensuring every gram of material maximizes its value. On Mars, nothing is truly waste, only resources in the wrong place. Mastering the art of recycling is the true test of our long-term viability on this distant world. On Mars, energy is life. Without a stable energy supply, all plans for survival and exploration would be nullified. Solar power appears the most obvious energy choice on Mars. Though farther from the Sun than Earth, Mars still receives sufficient sunlight intensity to drive highly efficient solar panels. In fact, from the earliest Viking landers to today's Perseverance rover, solar power has been the lifeline for numerous robotic missions. This success demonstrates the viability of solar technology on Mars, yet this reliance also exposes a fatal flaw. Mars frequent in prolonged dust storms. The tragic fate of the Opportunity rover stands as the most famous example. This compact rover, designed for a mere 90-day mission, survived an astonishing 15 years beyond its intended lifespan, thanks to its ingenious design and occasional dust devils clearing its panels, remarkably extended its service life to an astonishing 15 years. Yet in 2018, a massive global dust storm struck. The sky darkened as sunlight was completely blocked. Solar panels covered in thick dust could no longer generate sufficient power. Opportunity ultimately lost contact with Earth in the bitter cold. Its story is both heroic and tragic, sounding the loudest warning bell for future human missions. If such risks exist for a small rover, what of a full-fledged base relying on electricity to maintain air, water, temperature, and light? An energy disruption would spell instant catastrophe. Global dust storms can persist for weeks or even months. During such periods, solar power generation could plummet to less than 5% of normal levels. The base's battery reserves simply cannot sustain such prolonged darkness. Life support systems would cease functioning. Crops in the greenhouse would wither and die. Water circulation systems would freeze. Internal habitat temperatures would rapidly plummet to Mars's frigid extremes. This would undoubtedly lead to catastrophic consequences. Therefore, while solar power may serve as an auxiliary or supplementary energy source, it must never become the sole pillar upon which a human base relies for survival. We require a more powerful and reliable energy source, one that ignores the alternation of day and night, disregards seasonal shifts, and remains unaffected by the ravages of dust storms. We require an energy source capable of delivering hundreds or thousands of kilowatts of stable power for decades. This energy must be compact enough for transport from Earth, and capable of autonomous startup and operation within Mars' harsh environment. The answer points to nuclear power. When sunlight is obscured and wind power proves insufficient, nuclear fission becomes humanity's sole option for lighting a perpetual flame on Mars. Unlike solar and wind power, which depend on unpredictable weather, the core of a nuclear reactor is a highly controlled physical process. It releases immense energy by splitting heavy metal nuclei. This process occurs within a robust sealed container, virtually unaffected by external conditions. NASA has been actively developing nuclear fission systems for space applications. One of the most notable projects is the Kilopower system. The Kilopower project aims to develop a series of small, compact fission reactors. These reactors are roughly the size of a standard trash can, yet can sustainably provide 1 to 10 kilowatts of power for over 10 years of operation. Larger capacity versions based on kilopower technology, such as systems capable of outputting 40 kilowatts, are being planned for lunar and Martian missions. A single 40-kilowatt reactor would suffice to meet the basic power requirements of an initial 4-person Mars base, including life support systems, water recycling equipment, lighting, and scientific instruments. Should greater power be needed, for instance, to mass-produce rocket fuel, flexible power scaling can be achieved by deploying multiple reactor modules. These space nuclear reactors are ingeniously designed for safety. They utilize highly enriched uranium-235 as fuel, with a core composed of simple metal alloy structures, relying on the inherent physical properties of nuclear materials to passively regulate reaction rates. This makes them exceptionally stable and reliable. The process of starting such a reactor on Mars is nearly fully automated. It will be designed to activate autonomously upon arrival at Mars via commands from Earth. The radiation shielding layer surrounding the reactor is meticulously engineered, ensuring that radiation levels drop to normal Martian background levels several dozen meters away from the reactor, posing no additional threat to astronauts. Contrary to common perception, using nuclear energy on Mars is actually safer than on Earth, because it eliminates concerns about earthquakes, tsunamis, or any man-made catastrophic events. Mars itself serves as a vast natural containment zone. Beyond these fission reactors, another nuclear technology we've long mastered is the radiospike thermoelectric generator, or TCG. It does not rely on a fission chain reaction, but harnesses the heat generated by the natural decay of the radioactive element plutonium-238, directly converting it into electricity via thermocoulus. This is the principle behind the multi-purpose radio spy thermoelectric generator, or TCG. It provides stable, reliable power for the Curiosity and Perseverance rovers, enabling them to explore continuously for years, unaffected by sunlight or dust. It is an ideal power source for small devices. However, for human bases requiring power demands several orders of magnitude higher, only a fission reactor can deliver sufficient power. The greatest challenge in bringing nuclear energy to Mars' surface lies not in technical feasibility, but in political and public perception. It is essential to clearly communicate to the public that space-based nuclear systems operate on entirely different design philosophies and risk levels compared to terrestrial nuclear power plants. They undergo exceptionally rigorous safety testing, even in the most extreme launch failure scenarios. Fuel will not leak to cause environmental contamination. Once successfully deployed, these miniature reactors will revolutionize the energy landscape of Martian bases. They can be positioned at a safe distance from the main base. With power transmitted via cables, they can provide round clock power to water ice extraction units, supply massive amounts of electricity to propellant production plants, and maintain warmth and light in habitats and greenhouses. With nuclear power as the cornerstone, Mars bases will achieve unprecedented energy independence and stability. Astronauts will no longer need to panic at dust storms in the sky. They can focus with peace of mind on scientific exploration and base construction. This stable nuclear flame burning on the red planet will become the strongest guarantee for human civilization to take root in this new world. A stable, powerful power generation system is only half of the energy equation. The other half is how to safely and efficiently distribute this electricity to every corner of this emerging Martian community. The Mars base's power system will be a complex microgrid, requiring integration of multiple potential power sources, such as the primary nuclear reactor, supplementary solar panel arrays, and backup battery banks or fuel cells for emergencies. The core mission of this microgrid is first and foremost to guarantee absolute stability in power supply. Any significant voltage fluctuation or momentary outage could cause irreversible damage to precision life support equipment or scientific instruments. Given the unique characteristics of the Martian environment, the power system design will face unique challenges. Mars' atmosphere cannot dissipate heat as effectively as Earth's, so thermal radiation will be the primary means of heat dissipation. All power conversion equipment, transformers, and transmission lines must be specially designed for this. Additionally, the entire external power infrastructure must withstand dust ingress and material fatigue caused by extreme temperature cycles. High-voltage direct current HVDC is likely to be adopted for power transmission, as DC experiences lower losses over long distances and offers higher efficiency than alternating current AC. This is critical for a base requiring connections spanning several kilometers between different functional modules. The entire grid will be monitored and scheduled by an intelligent management system. This system can predict power demand in real time. For instance, when the water ice extraction plant begins operating at full capacity, or when astronauts conduct multiple high-energy experiments simultaneously. The system will automatically adjust power output and distribution priorities. This ensures critical systems like life support and habitat heating always receive sufficient power. Simultaneously, this grid must exhibit high redundancy and resilience. Should a transmission line fail due to dust storms or equipment malfunction, the system should automatically reroute power through backup lines to guarantee uninterrupted supply. The power network functions as the base's circulatory system, delivering the energy generated by its beating heart to every organ that requires it. A well-designed, robust energy network is the unsung hero enabling a Mars base to transition from survival to prosperity. For any crewed mission to Mars, the most costly resource is not the astronauts, not the habitat, nor the scientific equipment, but the rocket propellant required to return them to Earth. If all this propellant must be carried from Earth, the mission scale, cost, and complexity become prohibitively immense. This is why In-Situ resource utilization, ISRU technology, is so critical. It is hailed as a game-changing innovation. The core concept of ISRU is remarkably simple. Utilize resources already present on Mars to manufacture mission-critical products, thereby minimizing the cargo carried from Earth. The most vital ISRU application on Mars is propellant production, specifically manufacturing methane and liquid oxygen as rocket engine fuel and oxidizer. This process relies primarily on the abundant carbon dioxide in Mars' atmosphere and hydrogen extracted from subsurface water. The core technology is the Sabatier reaction. In this chemical process, carbon dioxide reacts with hydrogen under high temperatures and catalysts to produce methane and water. The chemical equation is expressed as CO for HCH2HR. The generated methane can be liquefied and stored as fuel. The resulting water can be electrolyzed into hydrogen and oxygen. The oxygen is liquefied and stored as an oxidizer, while the hydrogen is recovered and re-injected into the Sabatier reactor to initiate a new cycle. Through this ingenious closed-loop process, we produce the two primary propellants needed for Earth return, using only electricity, water, and Martian air. This ISRU system must begin operating long before the first astronauts arrive, and requires a massive, continuous power supply, potentially reaching tens or even hundreds of kilowatts. This further underscores the irreplaceable role of nuclear reactors. The system must operate continuously for nearly 1 Earth year to produce sufficient propellant to lift the ascent vehicle from the Martian surface into orbit. Only when the mission control system confirms the Martian surface propellant tanks are fully replenished will the command center on Earth finally authorize the crewed spacecraft's departure from Mars. This means astronauts know the moment they leave Earth that their ticket home from Mars is already secured. This forward-deployment strategy dramatically reduces the risks of crewed missions. ISRU isn't just about getting home. It represents a fundamental paradigm shift, from bringing everything from Earth to learning to utilize a new world's resources for survival and development. This is the first step in transforming Mars from an alien destination into our new home. On Earth, we live within a protective bubble formed by our magnetic field and atmosphere. On Mars, however, this shield is virtually non-existent. Astronauts will face constant exposure to the primary radiation threats, galactic cosmic rays originating beyond our solar system, and high-energy solar particles generated by occasional solar eruptions. Galactic cosmic rays consist of high-velocity atomic nuclei. Their immense energy and penetrating power. They can easily penetrate spacecraft and habitat walls, causing continuous microscopic damage to human cells and DNA. Long-term accumulations significantly increases the risk of cancer, cataracts, and central nervous system disorders. Although the radiation dose per unit time is low during multi-year Mars missions, this chronic exposure becomes a major health hazard. In contrast, solar high-energy particle events, though shorter in duration, their intensity can surge hundreds of times higher in an instant. If astronauts are conducting extravehicular activities during a solar flare, they could absorb dangerous or even lethal radiation doses within hours. Therefore, establishing a comprehensive radiation protection system is an absolute priority in mission design. The most direct and effective method against radiation is mass shielding, placing sufficiently thick materials between humans and radiation sources to absorb and block these high-energy particles. On Mars, the most ideal and inexpensive shielding material is Martian soil itself. Future Martian habitats will likely adopt subterranean structures or cover inflatable modules with several meters of Martian regolith. This red soylence and can effectively reduce radiation doses to relatively safe levels. Beyond this passive shielding approach, scientists are also researching more advanced active shielding technologies. The principle involves generating a localized strong magnetic field around spacecraft or habitats to mimic the protective effect of Earth's magnetic field and deflect charged particles. This technology remains in the experimental stage, but offers lighter, more flexible protection possibilities for long-term deep-space habitation. At the operational level, mission planning is also critical. Astronauts will carry personal radiation dosimeters to monitor their exposure levels in real time. Mission control centers will closely monitor solar activity. When intense solar proton events are forecasted, advance warnings are issued to astronauts on Mars. At such times, all personnel must enter designated radiation storm shelters. These are protected zones constructed with the heaviest materials, where astronauts can safely weather solar storms lasting hours or days. Through this multi-layered protective strategy, combining habitat design, technical measures, and mission management, we can keep radiation risks for Mars astronauts within acceptable limits. Though not entirely eliminable, this is sufficient to support their safe living and working on the Red Planet. If radiation tests the physical endurance of astronauts, psychological challenges represent the ultimate test of their will and spirit. Imagine yourself and 3 to 6 others, confined within a space totaling no more than a few dozen square meters, living and working continuously for over 2 years. You cannot step outside to breathe fresh air at will. You cannot feel the warmth of sunlight on your face. You cannot hear the rustle of wind through leaves. Every conversation with loved ones on Earth becomes an email requiring a 40-minute delay for a reply. This extreme environment combines isolation, confinement, and monotony, a condition unprecedented in human evolutionary history. Astronauts aboard the International Space Station can still gaze through portals at Earth's beauty and feel the solace of deep connection to home, while knowing they can return to Earth within hours in emergencies. On Mars, Earth appears only as a faint blue dot suspended in a pitch-black sky. Real-time communication delays sever all normal social ties. The profound loneliness would be unprecedented. In such conditions, minor friction could escalate into severe conflict, could become sources of stress. With no escape, negative emotions accumulate more easily, leading to diminished team cohesion and impaired decision-making. To understand and mitigate these psychological risks, NASA has conducted multiple simulation missions on Earth. The most renowned is the HI-SAS project in Hawaii, where volunteers live for up to a year in a domed habitat atop a volcano. When venturing outside, they must wear simulated spacesuits. Food consists of pre-packaged space rations. Communication with the outside world is time-delayed. These studies offer valuable insights. Researchers identified several critical factors for maintaining mental health. First is a sense of purpose and meaning in the mission. Astronauts must firmly believe in the value of their work. This helps them endure challenging moments. Second is personal space and privacy. Even within a confined shared environment, providing a small corner for solitude and personal belongings is vital for psychological relaxation. Third is food diversity and palatability. Enjoying a satisfying meal ranks among the most effective daily mood regulators. Fourth is maintaining meaningful connections with Earth. Even delayed video and audio messages significantly alleviate homesickness. Finally, team social activities and entertainment. Joint game nights, movie nights, or holiday celebrations can strengthen team bonds and create positive collective memories. Mission design will also incorporate psychological support measures. Adjustable LED lighting within the habitat will simulate Earth's circadian rhythms to aid sleep regulation. Virtual reality technology may temporarily immerse them in Earth's forest or beach vistas for brief psychological escape. Identify early signs of potential interpersonal tension, and prompt timely team counseling. Astronauts bound for Mars will undergo rigorous psychological screening and training. They will not only be top-tier scientists and engineers, but also emotionally stable, resilient, and T-oriented explorers. They must master conflict resolution techniques and possess high cultural sensitivity to navigate potential differences within an international crew. Ultimately, maintaining mental health on Mars is not merely about comfort, but directly impacts mission success and safety of every crew member. Our united, optimistic, and psychologically resilient team will be our most valuable asset on the Red Planet. On Earth, during medical emergencies, we can immediately call emergency services, and doctors can perform real -time diagnoses and surgeries. But on Mars, all this becomes incredibly complex and difficult. The most fundamental obstacle remains the 40-minute communication delay. By the time doctors at Earth's mission control see footage of an astronaut collapsing, over 20 minutes have already passed on Mars. And by the time Earth's emergency instructions are relayed back, another 20 minutes have elapsed. During this agonizing wait, the injured person's condition may have deteriorated drastically. Therefore, the Mars base must achieve an extremely high degree of medical autonomy. This means the astronaut crew must rely on their own capabilities to handle medical issues ranging from common illnesses to severe trauma. The crew traveling to Mars must include at least one member who has undergone advanced medical training far exceeding standard first-aid instruction. He or she will essentially serve as a battlefield surgeon, capable of performing complex trauma surgery, managing critical patients, and possessing not only surgical skills, but also master dental diagnostics, imaging, and pharmacology, as they will be the sole medical provider on Mars. The base will house a fully functional micro-hospital. This medical module will include advanced vital signs monitoring equipment, portable ultrasound and Dex-ray machines, a compact yet well-stocked pharmacy, and a sterile surgical bay. Crucially, it will feature a semi-autonomous surgical robot under the medical officer's supervision. This robot can provide exceptionally stable operations, reducing errors caused by human tremors, and potentially performing pre-programmed standard surgical procedures, thus assisting or even replacing human doctors in critical moments for precision maneuvers. To compensate for the lack of experts support due to communication delays, artificial intelligence will play a crucial role. The AI medical assistance system incorporates a vast medical database containing tens of thousands of disease symptom diagnosis pathways and treatment protocols. Once medical officers input patient symptoms, vital signs, and test results into the system, AI rapidly performs differential diagnoses and recommends optimal treatment protocols and medication dosages, effectively equipping Martian doctors with an indefatigable encyclopedic medical advisor. Though lacking real-time communication, telemedicine retains significant value. Mars medical officers can package high-definition wound images, ultrasound videos, and detailed medical data for transmission back to Earth. Although responses may take several tens of minutes to arrive, the consultation opinions and carefully considered treatment plans provided by Earth's assembled top medical experts across all fields remain an irreplaceable and invaluable resource. Daily health management is equally critical. Astronauts will wear undergarments made from smart fabrics that continuously monitor heart rate, body temperature, and even blood oxygen levels. Sensors within the cabin will also track their sleep quality and activity levels. All this data will be analyzed by AI systems aimed at detecting early signs of health abnormalities and intervening before problems escalate. Prevention is always better than cure. On Mars, this principle becomes a matter of survival. From common appendicitis to unexpected fractures, from severe infections to potential psychological crises, the Mars medical officer and his team must prepare for every contingency. Their training, their technology, and their unflappable courage together form the first and last line of defense for life on distant Mars. The human body is a precision machine evolved to adapt to Earth's gravity. When it enters the microgravity of space or the low gravity of Mars, a series of troubling adaptive issues arise. During the 6-to-9-month voyage to Mars, astronauts will remain in microgravity. Their bodies will immediately begin to change, with no need to constantly counteract gravity to support themselves. Muscles rapidly atrophy, especially the anti-gravity muscle groups in the lower limbs and back. Bones also lose calcium at a rate of 1 to 2% per month, leading to reduced bone density and increased fragility. The cardiovascular system becomes less efficient. The heart no longer needs to pump blood upward with the same effort required on Earth, resulting in weakened heart muscle and reduced total blood volume. Body fluids accumulate in the upper body and head, causing facial swelling and persistent nasal congestion. To counter these adverse effects, the spacecraft will be equipped with rigorous countermeasures. Astronauts must spend hours daily on specialized treadmills and resistance training equipment to simulate weight bearing through high intensity exercise, tricking the body into believing it still requires these muscles and bones. Simultaneously, they take specific medications, such as bisphosphonate, to help slow bone loss. Yet even these measures cannot fully halt bodily changes. When astronauts finally step onto the Martian surface after a long voyage, they will actually be in a physically weakened state, yet must immediately begin high-intensity-based construction and scientific exploration. This undoubtedly presents a tremendous challenge. Mars' gravity is only 38% of Earth's. For bodies emerging from a microgravity environment, this is both a relief and a new test. On one hand, they can finally feel support beneath their feet. Body fluids redistribute toward the lower limbs, and facial swelling subsides. Yet their muscles and bones remain fragile, and their cardiovascular systems struggle to rapidly adapt to the new gravitational environment. During their initial days on Mars, astronauts may experience unusual heaviness and fatigue. Even with Mars' lower gravity, their weakened bodies will find each step arduous, prone to rapid heart rates and dizziness. Thus, mission planning must include a gradual acclimatization period. During the first few weeks after arriving on Mars, astronauts' activity levels will be strictly controlled, while continuing intensive physical therapy and exercise to gradually rebuild muscle strength and bone density under Martian gravity. Looking further ahead, the long-term effects of prolonged exposure to low gravity remain a significant scientific unknown. We don't know whether bone and muscle loss will plateau after years of living on Mars or continue to worsen, nor do we understand how low gravity might affect vision, the endocrine system, or even fertility. To fundamentally address this challenge, scientists are seriously exploring the feasibility of equipping crewed Mars spacecraft with artificial gravity systems. One concept involves separating the habitat module from the propulsion section via a long tether, rotating the entire assembly to generate centrifugal force that mimics gravity, just as you feel water droplets being flung outward on a spinning umbrella. Astronauts inside the rotating cabin would experience a similar outward force resembling gravity if the rotation radius and speed are properly calibrated. This system could provide an Earth-like gravitational environment for months-long voyages, completely preventing the health deterioration caused by microgravity. Though this technology is highly complex and untested with humans, it may represent the ultimate solution for enabling long-term, healthy human interstellar travel. When astronauts finally return to Earth after a 2-year mission to Mars, they face their final and most challenging physical adjustment, readapting to Earth's full gravity. Their bodies, accustomed to Mars's weightlessness, will find walking on home soil akin to trudging through mud, each step feeling incredibly heavy. They would require weeks or even months of intensive rehabilitation training to regain normal walking and daily functioning on Earth, never fully recovering to pre-mission levels. Every journey to Mars pushes the boundaries of human physiology. Every lesson learned is not only to ensure astronauts return safely, but also to prepare for the day we can truly adapt and settle in that new gravitational world. Journeys to Mars cannot be initiated at will. They are strictly governed by the laws of celestial motion. These laws dictate the so-called launch window, a window of opportunity that opens only once every 20-6 months. Its underlying principle is the classic Homer transfer orbit in spaceflight dynamics. This trajectory minimizes fuel consumption for interplanetary transfer. As Earth and Mars orbit their respective paths, their relative distance constantly shifts. The principle of the Hohmann transfer involves launching a probe from Earth when Mars is precisely positioned about 45 degrees ahead of Earth. The probe then follows an elliptical orbit that tangentially touches both Earth's and Mars orbits. After approximately 9 months of travel, when the probe reaches the aphelion of its elliptical orbit, Mars will have precisely reached the same point, enabling a perfect orbital rendezvous. This exact geometric alignment occurs only once every 26 months. Missing a launch window means waiting over 2 years for the next opportunity. This cyclical constraint imposes immense time pressure and complexity on Mars mission planning. All system development, testing, and integration must strictly adhere to this cosmic timeline. Any delay could push the entire project back by years. Simply knowing when to launch is insufficient. We must also determine how to get there. The choice of transportation architect. This fundamentally addresses what propulsion system will we employ to traverse these hundreds of millions of kilometers. Currently, four primary options stand before engineers, each with distinct advantages and disadvantages. The first is the traditional all-chemical propulsion approach. This represents the most mature and conservative choice. It employs liquid rocket engines, similar to those used in the Apollo lunar missions, but on a larger scale, to perform several brief, powerful firings, to enter transfer orbit, perform mid-course corrections, and ultimately enter Mars orbit. The advantage of this approach is low technical risk with a simple, reliable system. However, the drawback is extremely low efficiency, requiring the carriage of massive amounts of propellant. This results in an exceptionally large initial mass launched from Earth and a prohibitively high mission cost. The second approach combines solar electric propulsion with chemical propulsion. Solar electric propulsion utilizes large solar panels to harvest energy. It ionizes and ejects inert gases like xenon at high velocity to generate a continuous minute thrust. This thrust is so small it cannot even be felt by hand. However, it continuously for months or even years. During prolonged interstellar cruising, it gradually accelerates, accumulating a significant velocity increment. When the spacecraft approaches Mars and requires braking maneuvers to enter orbit, high-efficiency traditional chemical rockets are then employed to execute high-thrust maneuvers. The advantage of this hybrid architecture is significant propellant savings, thereby reducing the total launch mass. However, the drawbacks include extended travel times and the risk of micrometeoroid and space debris impacts on the large solar array during transit through interplanetary space. The third approach combines nuclear electric propulsion with chemical propulsion. Its conceptual framework resembles the second option, but replaces solar panels with a small nuclear fission reactor to power the electric propulsion system, unaffected by distance from the sun. The nuclear reactor delivers more robust and stable power than solar arrays, enabling more efficient electric propulsion and potentially further reducing voyage duration. However, this technology also presents challenges, including heat dissipation issues for nuclear reactors in space environments, and political and public acceptance of nuclear systems in orbit. The fourth approach is nuclear thermal propulsion, a fundamentally different and highly promising concept, where a nuclear reactor directly heats propellants like liquid hydrogen, causing them to expand and eject at high velocity through a nozzle to generate thrust. Nuclear thermal rockets achieve roughly twice the efficiency of the best chemical rockets, meaning they can accomplish the same mission with less propellant, or carry more cargo with the same amount of propellant. It could drastically shorten travel time to Mars, potentially reducing a 1-way trip from 9 months to under 6 months. This is crucial for protecting astronauts from the hazards of prolonged space radiation and microgravity. However, nuclear thermal propulsion presents the highest technical difficulty. Although tested on Earth, it has never been implemented in space. It also faces political considerations regarding nuclear safety. Among all these architectures, SpaceX's Starship proposal stands apart, essentially falling within the realm of fully chemical propulsion. Its design philosophy aims to drastically reduce launch costs, through extreme reusability and mass production. Starship is engineered as a fully reusable transport system, with the goal of flying to Mars as frequently as commercial flights. This approach to mass transportation overcomes the inherent inefficiency of chemical propulsion, thereby transforming the mission's economic model. Beyond propulsion technology choices, mission planners must also decide between two fundamental mission types: conjunction-class missions and opposition-class missions. Conjunction-class missions utilize the most energy-efficient Hohmann transfer orbit, but require astronauts to remain on the Martian surface for an extended period, approximately 500 days, waiting for Earth and Mars to align again in a favorable relative position before commencing the return journey. The entire mission cycle spans roughly 900 to 1,000 days. The advantages of this mission type are -minimal total propellant requirement, -lower spacecraft performance demands. However, the drawbacks include -longest astronaut exposure to the Martian environment, including radiation and low gravity. Opposite -level missions employ higher -energy transfer orbits. They do not wait for the most ideal return window. Instead, by consuming more propellant, they shorten the duration of the Martian surface stay. The entire mission cycle can be reduced to 600 to 700 days. This may be more favorable for astronaut health, as it reduces total exposure time in deep space and on the Martian surface, but comes at the cost of requiring spacecraft to carry more propellant, or necessitating the adoption of more efficient, yet potentially less mature propulsion technologies such as nuclear thermal rockets. NASA and other space agencies are continuously analyzing these complex trade-offs. No single approach is flawless. The final choice will depend on a complex evaluation system, including technological maturity, acceptable risk levels, budget constraints, and the prioritizations of astronaut health. This decision will shape the entire landscape of human Mars exploration for decades to come. Whether we choose conservative chemical propulsion or embrace the riskier path of nuclear power, whether we opt for extended Mars stays for astronauts or pursue faster round trips, we are charting a precise roadmap for the most complex journey in our solar system. Every opening of a launch window marks a resolute stride toward our dream of becoming a multi-planetary species. Safely returning astronauts from the Martian surface to Earth represents the most critical and fragile link in the entire Mars mission chain. At the heart of this link lies the Mars Ascent Vehicle, a rocket specifically engineered for liftoff from Mars. It will carry mission-complete astronauts from the Martian surface to orbit Mars and rendezvous with the Earth return vehicle waiting there. This may sound like a replay of the Apollo lunar ascent stage liftoff from the Moon's surface, but the challenges of Mars ascent are vastly greater. Mars' gravity is over twice that of the Moon. This means launching the same mass into orbit requires significantly more energy in the larger rocket. Furthermore, while Mars is a thin atmosphere, the ascent vehicle must still traverse it, generating aerodynamic drag and heat, making the ascent process far more complex than on the vacuum of the Moon. Therefore, the Mars Ascent Vehicle will be a substantial spacecraft, approaching the size of the Apollo lunar module, or even larger. It must carry several tons of propellant, which ideally should not be transported from Earth, but instead produced in situ on Mars. This represents a key application of the ISRU technology we discussed earlier. Before astronauts arrive on Mars, pre-deployed ISRU plants would utilize carbon dioxide from the Martian atmosphere and hydrogen extracted from subsurface water to produce liquid oxygen and liquid methane propellants for the ascent vehicle. Through Sabatier reactions and electrolysis processes, these would then automatically refuel the ascent vehicle's tanks. When astronauts conclude their hundreds of days surface mission and prepare for their return journey, they must be absolutely certain that all systems on the ascent vehicle are fully operational and that the fuel tanks are completely filled. Any failure in propellant production or leakage from the tanks would be catastrophic, as there is no way to replenish such vast quantities of propellant on the Martian surface once the ascent vehicle is confirmed ready. the astronauts will transfer from the main habitat to the ascent vehicle's cabin. This process itself carries inherent risks. They must traverse the Martian environment in spacesuits to enter a craft that may have sat dormant for months or even years amidst Martian dust. The ascent process will be highly automated and strictly controlled by the flight computer. After engine ignition, the ascent vehicle will climb vertically and rapidly traverse Mars' lower atmosphere. During the initial ascent phase, aerodynamic drag becomes a factor requiring consideration. The vehicle's shape must minimize resistance as much as possible. As altitude increases and the atmosphere thins, the vehicle will gradually tilt to begin a gravity assist maneuver, converting its vertical velocity into the horizontal velocity needed for Mars orbit. This is a delicate balancing act, requiring significant propellant expenditure. The entire ascent could last tens of minutes before the vehicle precisely enters a planned parking orbit around Mars. Only then does the most critical phase begin, orbital rendezvous. In the parking orbit, the Mars ascent vehicle must locate and approach the Earth return vehicle that arrived months earlier and awaits in orbit. This Earth return vehicle is a larger spacecraft, carrying the life support systems, propellant, and living quarters needed for the journey back to Earth. It functions like a deep-space mothership, quietly awaiting its crew to dock and begin the homecoming voyage. The two spacecraft must achieve docking with extreme relative precision while traveling at speeds of several kilometers per second, in orbit hundreds of kilometers above the planet's surface. This process resembles the docking procedures at the International Space Station, with one fundamental difference. No ground control center can provide real-time assistance. All navigation calculations, radar ranging, and maneuvering control must be performed autonomously by both the ascent vehicle and the Earth return vehicle. They rely on an advanced autonomous rendezvous system. This system utilizes optical sensors and LiDAR to precisely measure the relative position and velocity between the two spacecraft. Through a series of small, precise engine pulses, they gradually close the gap and correct any errors. Ultimately, guided by mechanical docking mechanisms, they achieve a hard docking and form a secure connection. Once docking is successful and the seal is confirmed intact, the astronauts can open the hatch and transfer from the cramped Mars ascent vehicle to the more spacious and comfortable Earth return vehicle. They may spend some time transferring critical scientific samples and data from the ascent vehicle. The ascent vehicle will then be jettisoned and left in orbit. Having fulfilled its historic mission, it becomes yet another man-made object orbiting Mars. This successful rendezvous from the Martian surface to orbit is one of the mission's most nerve-wracking milestones. It is known as the point of no return, because if ascent fails, no rescue mission from Earth could arrive in time. The entire astronaut crew would be stranded on the Martian surface, their survival entirely dependent on the base's remaining resources until the next possible rescue window years later, and such a rescue mission itself would be extremely difficult to execute. Therefore, the reliability of the ascent vehicle and orbital rendezvous system was given the highest priority. Every component underwent testing far exceeding standard protocols and was designed with redundancy to ensure this vessel home can be trusted 100% at the most critical moment. Only when the astronauts finally board the Earth return capsule safely and begin preparing for the long journey home do they truly embark on their path back to Earth. Those few minutes of soaring skyward from the Martian red dust will become the most breathtaking and proudest moments of their lives when the Earth re-entry module carrying the astronauts finally pierces the planet's atmosphere and lands on tranquil ocean waters or a desert-surrounded landing pad. Their physical journey has concluded. Yet another equally formidable challenge has only just begun. That is the process of readapting to the full gravity of our blue planet and reintegrating into the familiar society they left behind years ago. For nearly 3 years their bodies underwent a peculiar gravitational odyssey. First months of microgravity during the journey to Mars, then nearly 500 days in Mars' low-gravity environment. Finally, months of microgravity again during the return to Earth. This complex gravitational sequence has profound and intricate effects on the human physiological system. In microgravity, The body no longer requires robust muscles and bones to counteract gravity. Thus, it efficiently unloads these seemingly unnecessary burdens. Anti-gravity muscles, such as those in the lower limbs and back, rapidly atrophy. Calcium continuously leaches from the bones, primarily excreted through urine, causing bone density to decrease at a rate of 1 to 2% per month. This renders the skeleton fragile, more akin to the state of osteoporosis in the elderly. The cardiovascular system also undergoes changes. In space, blood and bodily fluids no longer pull downward under gravity, but distribute evenly throughout the body, causing astronauts to frequently experience facial swelling and nasal congestion. Meanwhile, the heart, no longer needing to exert effort pumping blood upward, becomes somewhat lazy and weakened, and total blood volume also decreases. When the return capsule enters Earth's atmosphere at extreme speeds, astronauts once again experience the long-missed sensation of gravity. During deceleration, they may endure overloads of 4 to 5 gs, feeling as though a massive weight presses down on their chest, making breathing itself difficult. But this is merely the beginning. When the capsule hatch finally opens, the moment they truly set foot on Earth's soil is when the real test begins. Earth's gravity feels like an irresistible force, pinning their bodies firmly to the ground. Every movement becomes extraordinarily difficult. Even something as simple as rising from their seat may require assistance from others and be accompanied by dizziness. When attempting to walk, their legs feel as heavy as lead, and they stagger, struggling to maintain balance. This is because their muscles have lost the ability to easily support their body weight. Simultaneously, the vestibular system in their inner ears and the brain regions responsible for spatial awareness have adapted to that state after prolonged weightlessness. Now they must relearn and interpret signals under gravity. This process causes severe dizziness and spatial disorientation. They may feel the ground beneath them swaying, or suddenly lose balance while bending to pick something up. During the initial days and weeks after returning to Earth, astronauts are placed in a specialized medical rehabilitation center. This becomes their classroom for relearning how to live on Earth. The rehabilitation process is rigorous and progressive. Initially, they may still require wheelchairs for most activities, or brief standing and walking sessions supported by parallel bars. Physical therapists guide them through a series of carefully designed exercises aimed at reactivating and strengthening atrophied anti-gravity muscles. Aquatic therapy is often a crucial component, as water's buoyancy partially counteracts body weight, enabling astronauts to move with less stress on their joints and muscles. As strength gradually returns, the intensity and difficulty of training will steadily increase. Progress will shift from water to land, from assisted walking to independent walking, then to stair climbing and more complex coordination exercises. The entire rehabilitation process may last weeks or even months, and requires continuous medical monitoring. Doctors will track their recovery progress through regular bone density scans, muscle strength tests, and cardiovascular function assessments to track their recovery progress. Some physiological changes may be irreversible. For instance, some lost bone density may never fully recover. They may face slightly elevated fracture risks for the rest of their lives. Beyond physical readaptation, psychological reintegration presents significant challenges. During the Mars mission, they lived in a tightly knit group with an extremely focused objective, highly structured schedules, and close interpersonal bonds. Each member shared a core mission: survival and exploration. Upon returning to Earth, they are instantly thrust into a world of information overload, social complexity, and countless daily trivialities. This transition from extreme focus to overwhelming complexity can trigger a sense of alienation and overwhelm, known as re-entry culture shock. They may need time to relearn how to navigate casual social interactions, make choices among vast product offerings, or even cope with Earth's traffic noise and crowded spaces. Relationships with family and friends may also require readjustment during their years away. Children have grown up, loved ones may have aged, friends' loves have moved on. Reintegrating into these altered networks of relationships requires patience and understanding. Post-mission psychological support is an indispensable part of the recovery plan. Psychologists conduct regular sessions with them to help process potential emotional fluctuations, post-traumatic stress reactions, or profound nostalgia for the past mission. Some astronauts may experience a sense of loss, or even nostalgia for that distant red planet, where they experienced one of humanity's greatest adventures. From a scientific perspective, the return and recovery process of Mars astronauts itself presents an extraordinarily valuable research opportunity. They are the first humans to endure such prolonged exposure to mixed gravitational environments. Medical researchers will conduct follow-up studies spanning years or even lifetimes to meticulously document the recovery of their bodily systems. This data is invaluable. It will deepen our understanding of human physiological limits and provide crucial medical foundations for future extended interstellar voyages, such as missions to Jupiter or Saturn's moons. Their recovery experiences will directly inform countermeasure improvements, including designing more effective space exercise equipment, developing better nutritional formulas and pharmaceuticals, and refining post-mission rehabilitation protocols. When these astronauts finally complete their recovery and resume their lives on Earth, they will have undergone a profound transformation. They are not only heroes exploring the unknown, but also pioneering subjects in human physiology and psychology. Their bodies embody both the cost and reward of humanity becoming an interplanetary species. Their stories of safe return and successful readaptation will instill immense confidence in future generations, proving humanity not only has the capability to reach distant planets, but also to return home safely from them and apply everything we learn among the stars to build a better future. When charting a course to Mars, mission designers face a fundamental choice, one that defines the mission's rhythm, duration, and risk profile. This choice lies between a conjunction-phase mission and an opposition-phase mission. These two orbital mechanics architectures represent fundamentally different mission philosophies, one emphasizing economy and resource efficiency, the other prioritizing astronaut health and time costs. Let us first delve into the conjunction-phase mission, generally considered the baseline mission model. It strictly follows the most energy-efficient home and transfer principle in celestial mechanics. When Earth and Mars orbit in their respective paths, a fuel-efficient launch window exists. At this point, a probe launched from Earth can travel along an elliptical trajectory and rendezvous with Mars after approximately 9 months of flight. However, the astronauts' mission is not complete. They cannot immediately return to Earth because Earth has already moved to another distant orbital position. They must wait on the Martian surface for approximately 500 Martian days until Earth and Mars align again in a suitable relative position. Only then can the journey back to Earth commence. This return voyage also takes approximately 9 months. Thus, the total duration of a complete round-trip mission reaches a staggering 900 to 1,000 days, equivalent to 2.5 to 3 Earth years. The core advantage of this mission architecture lies in its unparalleled propellant efficiency. It maximizes the utilization of the planet's natural orbital motion by reserving rocket engine chemical energy for the most critical junctures. This minimizes the initial mass launched from Earth, thereby reducing the number of launches and overall mission costs. From an engineering perspective, this represents an exceptionally elegant and pragmatic solution. However, the cost is that astronauts must endure an extraordinarily prolonged mission cycle. They spend a total of approximately 18 months in microgravity during transit, accumulating cumulative exposure to deep space radiation. More critically, during their 5-100 day stay on Mars, while the low gravity environment partially mitigates the effects of microgravity, the radiation shielding on Mars is far inferior to Earth's, leaving them continuously exposed to galactic cosmic rays and solar flares. Psychologically, such prolonged separation from loved ones, friends, and society on Earth, while living in an isolated, confined environment, presents an ultimate test of crew psychological resilience and team cohesion. Supporters of the continuous mission argue that by optimizing habitat design, enhanced radiation protection, and refine psychological support systems to mitigate these long duration challenges. After all, establishing a Mars base is inherently designed for sustained habitation. Conducting a 500-day surface mission on the first attempt directly validates this objective, in stark contrast to the patient, long-term approach of the Lian mission. The opposition mission embodies a more radical and rapid philosophy, sometimes termed a short-day mission. This architecture does not wait for the most energy-efficient return window, but instead utilizes a higher energy trajectory for an earlier return, after astronauts complete relatively brief surface work, typically lasting 1 to 2 months. To achieve this faster orbital transfer, the spacecraft must either carry more propellant or employ more efficient propulsion systems, such as the nuclear thermal rocket currently under development. The specific impulse of a nuclear thermal rocket is approximately twice that of a conventional chemical rocket. This means it can generate greater velocity increments with the same propellant, enabling the selection of steeper, faster transfer trajectories. A typical opposition-class mission duration could be reduced to 600 to even 100 days, nearly a year shorter than a conjunction-class mission. The most compelling advantage of this architecture is its significant reduction in astronauts' total exposure time to deep space radiation and microgravity environment. Radiation exposure is directly proportional to mission duration. Reducing the mission by 1 year substantially lowers the lifetime risk of cancer and other radiation-related illnesses. Simultaneously, shorter microgravity exposure means less muscle atrophy and bone density loss. This simplifies post-return rehabilitation and reduces the risk of acute health events during the mission. Psychologically, shorter mission cycles means lighter psychological burdens and easier to maintain team morale. Astronauts know they'll return home sooner. This certainty itself provides powerful psychological support. However, the advantages of opposition-class missions come at the cost of immense engineering challenges. First, it requires more propellant. This directly increases the initial mass launched from Earth, potentially requiring multiple rocket launches to assemble this heavier spacecraft in orbit. Second, it may necessitate reliance on emerging technologies like nuclear thermal propulsion, which remain untested in deep space flight, introducing additional technical risks. Finally, with drastically reduced surface time on Mars, scientific exploration and base construction must be highly efficient. Astronauts would need to engage in high-intensity work almost immediately upon landing, with little time for acclimatization or adjustment, potentially increasing the risk of operational errors. Choosing between the conjunction and opposition missions is far from a simple technical decision. It involves a series of complex trade-offs. First is the consideration of astronaut health. Radiation exposure and microgravity effects are major health risks in long-duration spaceflight. The opposition mission directly reduces these risks by shortening the duration. However, proponents of the conjunction mission argue that by installing better radiation shielding on the spacecraft and habitat, and implementing stricter physical training regimens, can keep these risks within acceptable limits. Second is mission objectives. If the primary goal is in -depth scientific exploration and validation of long-term habitation technologies, the conjunction mission's 500-day surface residency is invaluable. It enables more comprehensive seasonal observations, longer distance geological surveys, and more thorough life support system testing. Conversely, if the primary objective is to validate crewed landing technology and the swift, safe return of astronauts, then the opposition mission is more suitable. Third is technological readiness. The conjunction mission's fully chemical propulsion scheme, relying on existing or slightly extended technologies, appears more prudent and reliable. The opposition mission, however, is often tied to more cutting-edge technologies like nuclear thermal propulsion, whose maturity and reliability still require time to validate. Fourth is economic cost. The conjunction mission may have lower propellant and launch costs, while opposition missions, though more expensive per mission, may allow for more frequent launches due to shorter cycles in long-term planning, thereby accelerating capability development. The final decision is likely not an either-or choice. but rather a phased evolutionary strategy. In the early stages of human Mars exploration, we may see a hybrid architecture, or first execute a short duration mission with a stronger emphasis on technology verification, focusing on mastering critical entry, descent, landing, and ascent EDL technologies. As experience accumulates and confidence grows, subsequent missions would gradually extend surface dwell times, eventually transitioning to crewed missions for long-term habitation. This incremental approach both mitigates initial risks and paves the way for ultimate objectives, regardless of the chosen path. In-depth research into both crewed and uncrewed missions significantly enriches our orbital mechanics knowledge and mission planning capabilities. They represent humanity's diverse wisdom and strategies in confronting the physical laws of the cosmos. One is an economical path that aligns with nature and leverages existing conditions. The other is a rapid approach that challenges limits, trading resources for time. This choice has no absolute right or wrong. It will ultimately depend on our species, technological capabilities, risk tolerance, and exploratory ambitions. At a specific point in history, when we finally make our choice and embark on the journey to Mars, the very orbit we adopt will speak volumes about the values and dreams of our era. When the first permanent Mars base rises from the crimson dust, it will represent more than a scientific outpost. It will be a seed destined to grow and alter the trajectory of human civilization. The expansion of this base will not be a simple scaling up process. It will be a profound metamorphosis from complete dependence on Earth to high self-sufficiency, the germination of an extraterrestrial civilization. We can divide this lengthy evolution into several intertwined phases, each marking a qualitative leap towards self-reliance. The first stage is the survival foundation period, commencing with the landing of the first astronauts. This phase may last 5 to 10 years. The base's core mission during this time is to validate critical technologies and sustain the astronauts' basic survival. The base remains small in scale, possibly consisting of only a few interconnected modules. Energy relies primarily on pre-deployed kilowatt-class nuclear reactors, supplemented by solar panel arrays. Water supply relies entirely on extraction of near- surface water ice and highly closed-loop recycling systems. Food production remains experimental, concentrated in small aeroponic or hydroponic modules, cultivating short cycle leafy greens to supplement pre-packaged rations and primarily serve psychological regulation for astronauts. At this stage, nearly all precision equipment, spare parts, and complex pharmaceuticals depend entirely on regular Earth-delivered resupply. The base population may be maintained between 4 and 12 individuals, primarily composed of scientists, engineers, and medical personnel, whose primary tasks involve conducting fundamental scientific research, maintaining increasingly complex space systems, and collecting critical data for the next expansion phase. At this stage, Earth's supply lines are literally lifelines. Any significant disruption could threaten the base's survival. The second phase is the consolidation and expansion period. This stage may begin with the first rotation of permanent personnel, lasting 10 to 20 years. The base will evolve from a small outpost into a fully functional micro-town. The most significant transformation occurs in energy. As energy demands grow, more powerful megawatt-class fission reactors may be constructed, or even pioneering research into utilizing Martian deuterium for nuclear fusion may commence. This substantial increase in power will radically expand the base's capability boundaries. In resource utilization, the scope of ISRU technology will explode, extending far beyond mere propellant and oxygen production. Robotic mining systems will commence extraction of metallic elements from Martian soil, such as iron, aluminum, and titanium, while establishing small scale smelting and processing facilities for producing essential construction materials and replacement parts. Agriculture will undergo a revolution as purpose-built pressurized greenhouses commence operations, utilizing modified Martian soil or more advanced hydroponic techniques to cultivate staple crops like potatoes, wheat, and soybeans at scale, alongside a wider variety of vegetables and fruits, partially self-sufficient in meeting the base's caloric and nutritional needs. This diversification of food sources will significantly enhance residents' quality of life and health. Simultaneously, biome and future technologies will begin utilizing engineered microorganisms or cells to produce pharmaceuticals, nutritional supplements, and even basic materials within fermentation tanks. The base population may grow to 50 to 100 people, giving rise to more complex social structures and preliminary labor division. Beyond core scientific and engineering personnel, specialized professionals in agriculture, construction, and manufacturing may emerge. The physical form of the base will evolve from a cluster of concentrated modules into a clearly zoned community, with distinct residential, research, agricultural, and industrial sectors. These areas will be connected via pressurized tunnels or sealed rovers. At this stage, Earth's resupply missions will gradually shift from delivering survival essentials to providing high-value technical equipment, data, and new personnel. The base's economic independence will begin to take root. Phase 3 self-sufficiency period. This represents the mature stage of Mars base development, potentially achieved gradually 30 years after establishment. At this point, the base will reach a critical milestone, achieving over 95% self-sufficiency in life-sustaining resources through closed-loop systems. This means that beyond cutting-edge chips and specialized equipment, unable to be locally manufactured, the base can utilize Martian resources and highly advanced recycling technologies to provide ample food, water, air, and energy. Large scale closed ecosystems will be established, where plants, animals, microorganisms, and humans form a complex, symbiotic network. Organic waste is fully recycled into fertilizer. Carbon dioxide is efficiently converted into oxygen and biomass. Water loss is reduced to negligible levels. Industrially, Mars manufacturing will possess formidable capabilities, utilizing locally mined and recycled metals, ceramics, and plastics, advanced 3D printing and automated machine tools to produce the vast majority of components required for self-maintenance and expansion. It will even be capable of manufacturing new rovers or construction robots. The base population could reach hundreds or even thousands, forming a truly self-sustaining community. Social structures will become more complete, with schools, medical centers, and cultural recreational facilities emerging to meet the needs of second- and third-generation Martian settlers. How these new humans born and raised on Mars will perceive their relationship with Earth will present an entirely new sociological challenge. At this stage, the relationship between the Mars base and Earth undergoes a fundamental shift. From unilateral dependence to a mutually beneficial partnership, Mars may begin exporting unique resources to Earth, such as isotopes more readily produced on the planet, or specialized materials and pharmaceuticals developed under its low-gravity environment. The rudiments of interstellar trade begin to emerge. The final phase is one of prosperity and hub functionality. This represents the envisioned future, a fully matured Martian society. By this point, the Mars base can no longer be called a base. It will have evolved into a city, or even a network of civilizations spanning multiple regions of Mars. Cities may be built within vast lava tubes, perfectly protected by natural rock ceilings, or feature magnificent domes constructed from high-strength composite materials. Inside, lush green parks and expansive living spaces will thrive. Energy supply will enter the post-fission era, perhaps powered by highly efficient and clean nuclear fusion, or vast supersolar farms covering extensive areas. Agriculture will achieve complete ecological sustainability, simulating Earth's ecosystems within large scale artificial biospheres, providing not only sustenance but also unparalleled psychological comfort and recreational space. By this stage, Martian civilization will possess comprehensive scientific research, educational, cultural, and industrial systems capable of independently conducting cutting-edge scientific research, design and construct spacecraft bound for the asteroid belt and even Jupiter's moons. It will become humanity's bridgehead and supply station for venturing deep into the solar system. Mars' low-gravity environment makes it an ideal shipyard for constructing and launching large interstellar spacecraft, because traveling from here to the outer solar system requires far less energy than departing from Earth. Mars will transform from a frontier requiring sustenance into a powerful, self-sustaining civilization node, forming a dual center of the human world alongside Earth's civilization. This grand blueprint from base to self-sufficient civilization, each step fraught with immense technical challenges and unknown risks, yet the future it points toward is a more resilient human civilization, a species no longer placing all its eggs in one basket. The expansion and self-sufficiency of the Mars base will be more than a triumph of engineering and biology. It will stand as the ultimate testament to human ingenuity, collaboration, and indomitable spirit. When we learn to rely entirely on ourselves on Mars, we not only ensure our species' survival in the cosmos, but also redefine the meaning of home. Home is no longer confined to a single planet, but extends to any place our civilization flame can illuminate and take root. Mars' ultimate value extends far beyond becoming a self-sustaining settlement. Its greater significance lies in serving as humanity's strategic gateway to other worlds within the solar system. This pivotal role stems from Mars' unique astronomical position and physical environment. First, from orbital mechanics, Mars occupies a critical position between the inner rocky planets and the outer giant planets of the solar system. It functions as a natural transit point in the vast solar ocean. Launching missions to the asteroid belt from Mars requires significantly less energy than direct launches from Earth. The asteroid belt, rich in metallic minerals and water ice, represents a treasure trove for future space industries. Mars could serve as an ideal logistics base and product processing center for developing these resources. Launching missions to the Jupiter system from Mars is also far more economical than launching from Earth. This orbital advantage makes Mars destined to become humanity's springboard for deep space exploration. Mars' low-gravity environment forms another cornerstone of its gateway function. Surface gravity on Mars is only 38% of Earth's. This gravitational level strikes a perfect balance, sufficient to maintain human physical health and avoid severe physiological issues caused by prolonged microgravity, while remaining significantly lower than Earth's gravity. Launching spacecraft into orbit from Mars' surface requires only about 40% of the energy needed for Earth launches. This means constructing and launching large interstellar spacecraft from Mars is significantly easier and more economical than doing so from Earth. Imagine future Martian shipyards building massive nuclear fusion-powered spacecraft in Martian orbit, unburdened by Earth's formidable gravitational well. These vessels can be designed larger and more complex, carrying greater scientific instrumentation and life support supplies to sustain multi-year exoplanetary exploration missions. Mars' resource endowment positions it to become a deep space exploration supply hub. We've already discussed Mars' potential to produce rocket propellants for spacecraft bound for more distant planets. Mars could serve as the perfect refueling station. A spacecraft departing Earth could arrive at Mars lightly loaded, refuel in Mars orbit using locally produced fuel, then depart fully energized for Jupiter or Saturn. This staged resupply strategy will fundamentally transform the mission architecture of solar system exploration, enabling previously unimaginable long-duration voyages. Beyond propellants, Mars can also provide other supplies essential for extended journeys, including food, water, and even 3D-printed replacement parts for spacecraft components. A self-sustaining Martian civilization will become a reliable rear base for deep space navigation. Let's outline a Mars-based exploration roadmap. Phase 1: Asteroid Belt Development. The average distance from Mars to the asteroid belt is significantly shorter than Earth's distance to the belt. Probes launched from Mars could reach asteroids faster. Future asteroid miners could establish Mars as their their operational hub for equipment maintenance and preliminary processing of mined minerals. Rare metals like platinum and water ice resources abundant on asteroids could be transported directly back to Mars to support local economic development, while Mars provides life support and industrial processing capabilities, forming a mutually beneficial space economic cycle. The second phase targets the Jupiter system. Jupiter boasts numerous intriguing moons, such as the icy Europa, which may conceal liquid oceans beneath its surface, and the volcanically active Io. While the journey from Mars to Jupiter still takes several years, it significantly increases mission feasibility compared to launching directly from Earth. Spacecraft using Mars as a base can carry more powerful energy systems and more robust life support, enabling long-term exploration of Jupiter's moons, and even laying the groundwork for future and outposts on these moons. The third phase will extend its reach into the Saturn system. Titan, Saturn's largest moon, boasts a dense atmosphere and lakes of liquid hydrocarbons, making it an ideal laboratory for studying probiotic chemical processes. Journeying from Mars to Saturn, though lengthy and challenging, will benefit greatly from Mars' logistical support, significantly boosting mission success rates. These outer planetary explorations will no longer be one-off ventures launched from Earth, but rather systematic exploration activities using Mars as a pivotal base. Mars' environment itself serves as an invaluable testing ground, offering the only available template for future planet terraforming. Closed-loop ecosystem technologies developed on Mars, radiation protection methods, low-gravity agriculture, will all be directly applied to future construction on other planets. Even research on creating life sustaining oases in barren Martian soil may one day inform the construction of high-altitude cloud cities on Venus or subaqueous bases on Europa. Mars will become humanity's university for learning to survive and thrive in alien worlds. Mars' gateway significance extends to the cultural realm. As human civilization takes root on Mars and begins journeying to more distant planets, our perspective will undergo a fundamental shift from single-planetary thinking to true solar-system thinking. Mars will give birth to a new generation of explorers, born on Mars, raised on Mars. They may retain cultural affinity for Earth, that their future lies among the broader cosmos. These children of Mars may pioneer exploration of the outer solar system, their bodies and minds more attuned to space environments, their technological culture designed from the outset for interstellar life. This process will redefine humanity's identity. When Earth and Mars both become human homelands, when we can freely traverse multiple worlds, we will truly become a solar species. Mars plays an irreplaceable bridging role in this historic transformation. It is neither too close to Earth like the Moon, nor as distant as the moons of outer planets. It is the first place beyond Earth's cradle we can truly call a new home, and the springboard from which we leap to other worlds, gazing at the stars from Mars. Jupiter will no longer be a mere bright point in the night sky, but a destination within reach. Saturn's rings will cease to be a spectacle only seen through telescopes, and instead become a majestic sight for future explorers to behold firsthand. The asteroid belt will transform from a distant obstacle into a treasure trove of resources brimming with opportunity. This shift in perspective, this cognitive revolution that places the entire solar system within our grasp, is the profound significance of Mars as a gateway in the blueprint for future solar system civilization. Mars will play a role akin to port cities during the age of exploration. It will be both the departure point for exploring the unknown and the hub where knowledge and wealth converge. It will serve as a testing ground for new technologies and a cradle for new cultures. Through Mars, human civilization will complete its third great expansion, from land to sea to the stars. The scale and significance of this expansion will far exceed the sum of all previous explorations. The moment we establish permanent settlements on Mars, we will unlock not merely a new world, but the gateway to the entire solar system. Beyond that threshold lie boundless possibilities and stars awaiting discovery. Mars transforms humanity from Earth's inhabitants into citizens of the solar system. This shift in identity may be the most precious treasure we harvest from the red planet. When humanity establishes its first permanent settlement on Mars, our challenges will shift from mere arrival and survival to sustaining life and thriving on this new world. Sustainability will cease to be an abstract concept and become a practical imperative for civilization survival. It demands a fundamental rethinking of resource utilization, energy production, waste management, and ecological balance. To build a self-sustaining model of civilization, the core of achieving sustainable development on Mars lies in establishing a perfect closed-loop system. On Earth, we can rely on the global biosphere to purify air, recycle water, and regenerate resources. But in Mars's isolated environment, we must use technology to recreate these ecological functions. This means we need to develop technologies that fully convert human waste into fertilizer, systems that purify wastewater into drinking water, and processes that efficiently convert carbon dioxide into oxygen and biomass. The conversion efficiency of each process must approach 100%. Any leakage or loss would necessitate replenishing resources from Earth, preventing the settlement from ever achieving true self-sufficiency. Energy is the cornerstone of sustainable development. Mars settlements cannot rely on fossil fuels, but must establish a diversified clean energy system. Nuclear fission reactors can provide base-load power, especially during the long Martian nights and global dust storms. Solar array fields can be distributed across vast areas to mitigate the impact of localized dust coverage. Future technologies may also harness Martian wind energy. Despite the thin Martian atmosphere, persistent wind currents can still be converted into useful power. Redundant design of the energy system is critical to ensure that failure of any single system does not cause the collapse of life support. Sustainable water management is particularly crucial. Every drop of water on Mars is precious. We must establish a complete water cycle system from extraction to recycling. Water extracted from subsurface ice will be used for drinking, agriculture, and industrial purposes. Wastewater will undergo multi-stage purification processes, including mechanical filtration, reverse osmosis, and advanced oxidation processes, to ultimately return as purified water. Even water vapor exhaled by astronauts in sweat will be collected and reintroduced into the cycle. This system aims to maintain water loss rates below 1%, achieving near-perfect water recycling. Food production systems also require redesign. Traditional monoculture farming is unsuitable for space environments. We must develop integrated agroecological systems, combining plant cultivation, fish farming, and microbial production. Within these artificial ecosystems, plant growth provides oxygen and partial sustenance for fish. Fish excrement supplies nutrients to plants. Microorganisms decompose organic waste, forming a miniature self-sustaining cycle. Such systems not only provide food, but also help regulate air composition and recycle waste. Material science plays a vital role in sustainability. We must develop technologies to utilize local Martian resources. For manufacturing and construction, Martian soil can be used for 3D-printed building structures. Subsurface deposits can provide metals and other construction materials. More importantly, we need to establish comprehensive material recycling systems. Any discarded equipment or structures should be disassembled and reused, rather than becoming accumulated waste. This requires considering product recyclability from the design phase, using standardized modules and easily separable materials. Sustainability also encompasses social and cultural dimensions. A healthy society requires work-life balance, access to education, healthcare, and cultural activities. Within Mars's closed environment, maintaining residents' mental health is equally vital. This necessitates designing comfortable living spaces, providing communication facilities to maintain Earth connections, and creating diverse recreational and social activities. Social sustainability further entails establishing equitable resource distribution mechanisms and inclusive decision-making processes, ensuring every member can contribute to the community and share in the fruits of development. Innovation in economic models is also key to sustainability. Traditional growth-oriented economic models are no longer applicable in Mars resource-limited environment. We must explore steady-state economic models, where the focus is not on infinite growth, but on pursuing enhanced quality of life through balance. Mars economy may be based on resource efficiency and systemic circularity as primary metrics, rather than traditional gross production value. Such models prioritize long-term stability over short-term profits. The educational system must cultivate a new generation of Martian residents who not only master science and technology, but also deeply understand ecological principles and systems thinking. Having grown up in a closed environment, they will inherently grasp the preciousness of resources and the importance of recycling. This new Martian generation may develop values and worldviews fundamentally different from Earth's, with greater emphasis on collective well-being and long-term planning. International cooperation is indispensable for sustainable space development. No single nation can bear the immense cost of building a sustainable extraterrestrial civilization alone. We must establish a global cooperative framework to share technical standards and best practices. This is not only a technical necessity, but also a symbol of humanity's shared future. Replicating Earth's geopolitical rivalries on Mars would contradict our very purpose of becoming a multi-planetary species. From a broader perspective, achieving sustainable development on Mars is not merely about survival on this specific planet. It's about testing and refining a new model of civilization, one that could ultimately be applied to Earth to help us address our environmental challenges. Water management techniques learned on Mars could be applied to Earth's arid regions. Knowledge gained from developing closed-loop ecosystems could inform vertical farming and urban design on Earth. Energy innovations could accelerate Earth's transition to clean energy. Most importantly, sustainable practices on Mars will demonstrate humanity's capacity to build thriving civilizations while respecting planetary boundaries. This will give us confidence and hope that progress need not rely on resource depletion, but can instead foster harmony with our environment. Whether on Earth or Mars, when we successfully establish a truly sustainable civilization on Mars, we will prove to the cosmos that humanity is not merely a species capable of exploring the stars, but a wise life form that understands how to coexist with the cosmos. The significance of this transformation far surpasses any technological breakthrough or scientific discovery. It signifies the maturation of human civilization, from the reckless consumption of adolescence into the rational equilibrium of adulthood. A sustainable Martian civilization will become the blueprint for humanity's journey to more distant stars. It demonstrates not only where we can go, but how we get there, and how we live once we arrive. This wisdom may become humanity's most precious legacy. To the cosmos, the green civilization built upon Mars' red soil will ultimately reflect back upon Earth, inspiring us to re-examine our relationship with our home planet. The experiences of two worlds will learn from each other. The wisdom of two civilizations will nourish one another, together pointing toward a brighter future, where humanity neither forgets its earthly roots, nor loses its cosmic dreams. This is the ultimate meaning of sustainable space development. It concerns not merely survival on another planet, but the growth and evolution of our species. As we learn to live sustainably on Mars, we also learn how to better protect Earth, how to become responsible beings in the cosmos. This dual awakening may be the most precious gift space exploration offers us.